In this video, we're going to analyze medians and altitudes of triangles and determine their points of concurrency. First, remember what a median is. It's a segment connecting a vertex of a triangle to the midpoint of the opposite side. So in this triangle here, an example of a median would be this red dotted line from the vertex to the opposite side's midpoint. We also have two other medians. The green and blue dotted lines are the medians from the other two vertices, and they do cut the sides in half. We can see the medians in this picture ABC, where all of those medians are concurrent at the single point here. No matter where I move my triangle, those medians are always going to be concurrent. They intersect at this point. This point of concurrency for medians is called the centroid. The centroid theorem describes the relationship between that centroid point and the segment that it lies on. That centroid is going to be 2/3 of the distance from the vertex to the side. Right. Down below I have a little illustration to show the relationship. So currently I have my medians of the triangle in green, showing the congruent parts on each side. Now to show the centroid, and what I'm going to do is I'm going to split up the medians into smaller distances. So notice here I have 6.8 as the length of this segment that I have highlighted. The other part of that median is 12.96. Notice the relationship between 6.48 and 12.96 is 6.48 is half of 12.96. Now notice when I check this last box, what it actually does is split those segments into 3 congruent parts. So I have 6.48, 6.48, and 6.48. That means the centroid is 2/3 from the vertex and 1/3 away from the side. Even when I move my triangle around, I can still see that no matter which median I'm looking at, that centroid is 2/3 away from the vertex. Okay, we're going to use that relationship here. In triangle ABC, Q is the centroid and BE is 9. Find the measure of BQ and QE. Well, BE is the length of that entire median. So I know that BQ is 2/3 of the way, and QE is 1/3 of the way of that median. So I want to find BQ, so I can take 2/3 of 9, or 2/3 of 9 is just 6. Now I also know that BQ plus QE is equal to 9. So 6 plus QE is equal to 9, so QE has to be 3. I could have also just taken 1/3 of BE to get 3 for the measure of QE. Down here I want you to try 1A and 1B using that same triangle ABC. Given that the measure of FC is 15, find the length of FQ and QC. Now we're going to talk about altitudes. Remember, an altitude is a segment connecting a vertex to the point on the opposite side, creating a 90-degree angle. So in this triangle here, segment BD is my altitude from that vertex straight down perpendicular to that opposite side. In this obtuse triangle, however, we have to make a side extension to be able to drop that altitude and find the height. In this triangle ABC, I'm going to show you the altitudes. Notice the altitudes are all concurrent at this blue point here. As I move the vertices of the triangle around, I can see that that concurrency point also moves, but notice it's staying inside the triangle here. If I make my triangle a different type of triangle, for example, if I make it a right triangle, notice my point of concurrency is on the triangle, actually is the right angle of the triangle. Notice if I make my triangle obtuse, that point of concurrency is now outside of the triangle. The point of concurrency of the altitudes is called the orthocenter. The lines containing the altitudes AF, CD, and BG intersect at point P, and we would call that the orthocenter. In this example, we're going to use coordinate geometry to actually find the location of the orthocenter using triangle FGH. To locate the orthocenter, I need to locate the altitudes of the triangle and then find the point of intersection of those altitudes. So my strategy here is to find the equations of two of the altitudes and determine their point of concurrency. So first, step one, find the equation of one of the altitudes. Well, I know because FG is horizontal, the altitude connecting point H to FG will be the vertical line through H. So therefore the equation will be x equals 1. So this vertical line is the altitude connecting H to side FG. And now step 2, I want to find the equation of one of the remaining altitudes. I've chosen to find the one from F to GH. So you have to find the equation of the line that passes through point F but is perpendicular to side GH. So you have to determine the slope of GH and then find the negative reciprocal of it. So the slope of GH is 2, so the slope of the altitude will be negative 1/2. Using the point slope form, I get the equation y minus 4 equals negative 1/2 times x plus 2. Distribute your negative 1/2 and add 4. So the equation of the altitude from F to side GH is y equals negative 1/2 x plus 3. Now, because the x value of this intersection has to lie on the vertical line, we know the x value of that intersection is 1. We can plug 1 into our other equation and we get positive 2.5. So we know our orthocenter is located at 1, 2.5.